Hello, and welcome to our lesson on sequences. Today, we're going to explore this fundamental concept that underpins much of mathematical problem-solving and pattern recognition. In this lesson, we will first understand what a sequence is. Then we will learn to generate terms in a sequence. Following this, we'll look at some examples to apply this new knowledge and reinforce our understanding. Learning how to clearly define and work with sequences will allow us to describe and solve problems more efficiently. For example, if you ever need to find the 50th term in a repeating pattern or verify whether a certain number is part of a specific sequence, these techniques will be invaluable. Let's start by understanding what a sequence is. A sequence is a list of numbers ordered in a specific way. This order is often determined by a mathematical rule or expression. For example, look at these sequences. First, 2, 4, 6, 8, 10, then 1, 3, 5, 7, 9. Can you see the pattern in each sequence? Let's break them down. In the first sequence, each term increases by 2. In the second sequence, each term increases by 3. These are examples of an arithmetic sequence. In an arithmetic sequence, each term increases by a constant difference. So for the first sequence, since each term increases by 2, this is an arithmetic sequence with common difference 2. The second sequence is an arithmetic sequence with common difference 3. To describe an arithmetic sequence mathematically, we can say it is of the form a plus di plus 2d, a plus 3d, and so on, where a is the first term and d is the common difference. Let's look at another sequence, 1, 4, 9, 16, 25. In this sequence, each term is the square of its position in the sequence. This is an example of a quadratic sequence. Quadratic sequences always include an n-squared term. In a quadratic sequence, the difference between the terms is not constant. This sequence is the square numbers. How are sequences different from the other algebraic concepts we have already learned? The key difference between sequences and expressions, equations, identities, and inequalities is in what they represent and how they are used. Expressions are combinations of variables and constants. For example, 2n plus 3. Equations state that two expressions are equal. For example, 2n plus 3 equals 11. Identities are equations that are true for all values of the variables involved. Inequalities compare two expressions, for example, 2n plus 3 is greater than 7. Sequences, however, are ordered collections of numbers formed according to a specific rule, which does not require solving or rearranging, but rather understanding and following the pattern. There are two key ways to describe the pattern of a sequence. First, the nth term formula, which gives the value of the term at any position n in the sequence. For example, if the nth term formula is 2n plus 10, then we can substitute in any value of n to find that term in the sequence. To find the first term in the sequence, we substitute 1 into the formula to get 12. If we wanted to find the 100th term of the sequence, we do not need to write out all 100 numbers in the sequence. Instead, we can just substitute n equals 100 into the formula to find that the 100th term is 210. The term-to-term rule describes how to get from one term to the next using the previous terms. For example, suppose we are told that the term-to-term rule is previous term minus 3. If we are given the sequence 25, 22, 18, we can find the next term by doing 18 minus 3, which equals 15. When we have a term-to-term rule to describe a sequence, we also need to specify the first term in order to uniquely determine the sequence. In other cases, we may be given a sequence and asked to find the nth term formula or the term-to-term rule. For example, consider the sequence 2, 4, 6, 8, 10. The nth term here is described by the formula 2n. If we use a term-to-term rule, we could describe it as the next term equals the previous term plus 2. Let's now use these concepts to generate sequences. Suppose we are given an nth term formula n squared and asked to generate the first 4 terms of the sequence. To solve this, we substitute in n equals 1, n equals 2, n equals 3, and n equals 4 into the nth term formula. The first term is 1 squared, which equals 1. The second term is 2 squared, which is 4. The third term is 3 squared, which is 9. And the fourth term is 4 squared, which is 16. We have therefore found the first 4 terms of the sequence. Now let's use the same nth term formula n squared to generate larger numbers. Let's generate the 10th term and the 20th term of this sequence. Substitute n equals 10 into the formula, we get 10 squared, which is 100. Substituting n equals 20 into the formula, we get 20 squared, which is 400. This demonstrates how useful the nth term formula can be for finding terms even very far down in the sequence without having to list all previous terms. Now let's generate a sequence using a term-to-term rule. Consider the sequence where the next term is the sum of the previous 2 terms and the first 2 terms are 0 and 1. This is called the Fibonacci sequence. Let's generate the first 6 terms of this sequence. We will start with the first 2 terms, 0 and 1. To find the third term, we must add the first 2 terms together, so we get 1 again. For the fourth term, we add together the first and second terms, so we get 2. For the fifth term, we add together 1 and 2 to get 3. For the sixth term, we add 2 and 3 to get 5. So these are the first 5 terms of the Fibonacci sequence. The Fibonacci sequence is significant in mathematics due to its unique properties and its appearance in various natural phenomena. The ratio between successive Fibonacci numbers approximates the golden ratio, which is approximately 1.618. This is a number that has fascinated mathematicians, scientists, and artists for centuries due to its aesthetically pleasing properties. The Fibonacci sequence can be found in the arrangement of leaves on a stem, the branching of trees, the spiral patterns of shells, and even in the reproductive patterns of rabbits. For instance, the number of petals on a flower often corresponds to a Fibonacci number, and the pattern of seeds in a sunflower is arranged in a spiral, with the number of spirals typically being consecutive Fibonacci numbers. Its presence in nature illustrates the inherent mathematical order and patterns in the world around us, making it a fascinating topic of study that bridges the gap between abstract mathematics and the observable universe. Moving on to using a term-to-term rule, imagine we have the nth term as 2 times the n minus 1 term minus the n minus 2 term. We are told that term 1 and term 2 are 1 and 2 respectively, so we can write this down. Now let's calculate the third term using the term-to-term rule. Substitute n for 3 in the term-to-term rule like this. And then we can simplify this to find that we have 2 times the second term minus the first term. This gives us 3. We can then do the same calculation for the fourth term to find that the fourth term is 4. This sequence would be 1, 2, 3, 4. Notice that this is an arithmetic sequence which adds 1 each time. So it is indeed possible to produce an arithmetic rule from a term-to-term rule. Try to see if you can find the nth term formula for this sequence, which is a fairly simple one. In summary, we have explored what a sequence is, how to generate terms with both the nth term formula and term-to-term rules. We've also seen how sequences differ from expressions, equations, identities, and inequalities. Now let's dive into some examples to get hands-on practice. Consider the arithmetic sequence, 2, 5, 8, 11. Find the next term. Remember, in an arithmetic sequence, each term increases by a constant difference. Here, that difference is 3. To find the next term in the sequence, we take the last term, which is 11, and add the common difference of 3. So the next term is 14. Now let's find the 10th term in the arithmetic sequence, 4, 9, 14, 19. The formula to find the nth term in an arithmetic sequence is nth term equals a plus n minus 1 times d. In this formula, ai is the first term in the sequence and d represents the common difference. So for our sequence, to find the nth term, we first need to identify the first term, which is 4, and the common difference, which is 5. Hence, the formula for the nth term of our sequence is that the nth term equals 4 plus n minus 1 times 5. For the 10th term, we sub in n equals 10. This simplifies to 4 plus 9 times 5, which gives us an answer of 49. In our final example, we will identify a term in a sequence. Consider the following sequence, 1, 4, 9, 16. Suppose we want to find whether 25 is in the sequence. First, notice that this is a sequence of square numbers. Then find the square root of 25, which is 5. Therefore, 25 will be in the sequence when n equals 5. In today's lesson, we explored the concept of sequences, an essential topic in algebra. We began by defining a sequence as an ordered list of numbers determined by a specific rule or expression. We examined different types of sequences, such as arithmetic and quadratic sequences, and discussed how they differ from other algebraic concepts like expressions, equations, identities, and inequalities. We learned how sequences can be described using the nth term formula, which allows us to find the value of any term based on its position, and the term-to-term rule, which describes how to derive the next term from the previous ones. Overall, we have established a solid understanding of sequence and how to work with them, setting the stage for more advanced algebraic problem solving. Watch the rest of the GCSE Maths course at Sophos Education.